Welcome back to Artcraft Electronics videos. A simple solar-powered battery charger system, Part 2. In Part 1 of this series, we selected a solar charge controller from Victron, using a set of specifications that may have seemed a little mysterious at the time. So where did those specifications actually come from? The answer takes us directly into the world of battery specifications, because in a solar charging system, everything starts with the battery itself. From the battery to the solar panels, the specifications define the entire system. So hang on, Part 2 reveals all. After researching Amazon reviews and comparing pricing, the point where value and performance intersected led me to the Elefast 12.8 volt, 100 amp hour LiFePO 4 battery. According to the manufacturer, the Elefast 12.8 volt, 100 amp hour battery is a high-performance lithium iron phosphate battery designed for deep cycle applications. It features an advanced battery management system, or BMS, with Bluetooth connectivity for enhanced monitoring and protection. Well now, I'm impressed. And it was cost-effective. As of May 17th, 2026, this battery was on sale at Amazon for about $169. Now let's take a closer look at what makes this battery interesting. We mentioned the battery management system, or BMS. Well, that provides protection against overcharge, overdischarge, overcurrent, short circuits, high temperature conditions above approximately 65 degrees Celsius, low temperature charging below freezing. So what does that all really mean? To me, it means a battery is designed to survive real-world use under varying conditions without becoming an expensive paperweight. And just to be clear, Elefast did not sponsor this video or provide the battery. What they did provide was a strong set of specifications and performance characteristics that made this battery my choice. One very important specification is the allowable charging current of 50 amps, along with charging voltage of 14.6 volts. As I mentioned in Part 1, I already have a utility mains-powered LiFePO 4 charger system that delivers 20 amps at 14.5 volts, and it performs very well. So it made sense to define our solar charge controller capability of about 20 amps, so we would have similar performance between those two systems. And just like that, we've defined one of the major design parameters, actually several parameters. Another critical requirement is the ability to precisely configure the charging characteristics for a LiFePO 4 battery. The Victron Smart Solar 120 handles this very well. Exactly how we configure those settings will be demonstrated later during the smoke test phase of the project. So now we have a battery and a method to charge it. But what powers the solar charge controller? Well, solar panels, of course. And possibly a utility-powered charging source as well. Maybe we'll add that when we get the solar charging part done. So let's look at the requirements for the solar input side of the system. So, how many solar panels are necessary to charge a LiFePO 4 battery? Well, I'm glad you asked. Let's work it out. Some viewers may not be familiar with the term sun hours. A sun hour equals 1,000 watts per square meter. This is not an hour in the sun in all areas of the world or even at all altitudes. I suppose there's some place in the world that an hour in the sun equals a sun hour, but I don't know where that would be. I do know that at 6,300 feet above sea level in May, when the sun is out, we get about 7 hours of sunlight in a given day, considering passing clouds and that low-flying C-130 I referred to earlier. So, if we take the 7 hours of full sunlight and want to get 650 watts per meter squared, we get 4.5 sun hours required. Wait a minute. How many sun hours do we need to charge a LiFePO4 battery? Why, we take the battery voltage, 12.8 volts, multiplied by the amp hours at full charge, that's 100, and we get 1,280 watt hours. So, our solar panels should provide 1,280 watt hours in 4.5 sun hours. That's it then. Well, sort of. We have a little bit more calculating to do and specifications to specify. We do have to consider the efficiency of the charger and the battery itself. That's 0.95 efficiency of the charger. It's a good, very efficient charger. And the battery is another 0.95. So our efficiency factor is 1 divided by 0.9, which is 1.11. So our factor, we need to multiply our calculation by 1.11. 285 watts times 1.11 equals 316 watts of solar panels. Remember? That's what we're calculating. Yeah. Yes, we have to allow that there are differences in locations we are trying to accommodate, and the fact that we probably are not going to discharge a battery completely. I don't think the BMS will allow you to do that. I'm not sure, though. I'll have to go back and check. So, we make what's called in engineering informed approximations, abbreviated WAG, and say we want at least 250 watts of panels. Worst case, we would require 2 days to fully charge it if we had only a 200 watt panel. However, 2 times 200 watt panels, 2 times a 200 watt panel would be perfect to charge that LiFePO4 battery in a day. That's enough solar power being generated to do the job, or we can use a single panel if our battery simply needs to be topped off after moderate use. We have calculated the ideal and included several variables to accommodate most places in the world. Abu Dhabi or Phoenix, you could probably do the job on a single panel. And in Alaska or Greenland, most of the year, you would probably need 2. We have included the efficiency of the charger and the battery, so let's agree on 400 watts for maximum flexibility, 200 watt solar panels. That's our choice. After researching the solar panels online, a selection was made. The Colsun TopCon bifacial 200 watt N-type solar panel appeared to check all the boxes. Here are the key specifications per panel. Maximum power 200 watts. Open circuit voltage 27.31 volts. Working voltage 23.74 volts working current 8.43 amps, and maximum current capability 8.9 amps. The maximum series fuse rating is 15 amps. That specification will come in handy in Part 3. Just to verify the numbers, 23.74 volts multiplied by 8.43 amps gives us approximately 200 watts. The math checks out. Technically, this project could operate from a single panel. It would just take longer to charge. But using two panels allows us to overpanel the charge controller some, and it'll help provide more consistent charging performance under varying sunlight conditions. We have a winner. As of May 17th, 2026, a two-panel 400-watt Colsun TopCon bifacial array could be found on Amazon for approximately $309. Could you get by with a single panel? Yeah, absolutely. But if the goal is charging at roughly 400 watts, that's 20 volts at 20 amps, then a 400-watt PV array makes very good sense. Now, I know we got pretty deep into the weeds today with specifications, calculations, and design requirements. But this is exactly what is necessary to properly design and even a simple solar charging system. So let's review our project parts list as of May 17th, 2026. We have a Victron Smart Solar 120 charge controller, and that's approximately $90 from Amazon or Inverters R Us. Our battery is an Elifast 12.8 volt 100 amp hour LiFePO 4 battery. That's approximately $169 from Amazon. And the solar panels that we just tortured ourselves over are the Colsun TopCon bifacial 400-watt PV array, and it was approximately $309 from Amazon. I don't remember the exact price. So, that's a wrap for Part 2. We wanted a battery and solar panels, and now we have them. This is shaping up to be a very solid emergency backup camping or vehicular solar charging system. Stay tuned for Part 3, where we'll define PV disconnects, battery breakers and disconnects, wire sizing, connectors, and pulling the whole deal together. See you then. Thanks to all those who have subscribed. Oh yeah, selecting notifications would probably be a good thing too, so you get all the parts in this series.